In this video, I'm going to talk about something very important in the context of conducting inferential statistics, and it's something known as family-wise error rate. Before I carry on with defining and explaining how to calculate family-wise error rate, I'm going to discuss some more elementary concepts that I've covered already. One of which is the fact that researchers specify an alpha level for each statistical analysis that they conduct. Remember that researchers usually use alpha 0.05 for any particular analysis that they conduct that's statistical in nature and is inferential, and you're wanting to go from the sample to the population. And alpha corresponds to the maximum level of chance one is willing to accept with respect to rejecting the null hypothesis erroneously. So stated alternatively, when a researcher conducts an analysis, they want to protect themselves from saying that there's something going on in the population based on their sample, when in fact nothing is really going on in the population. There is no difference between the groups, or there is no relationship between the two variables. Researchers want to protect themselves from committing an error that's saying that there is something going on, when in fact nothing's going on. And researchers accept a maximum 5% chance 5 times out of 100 of making that sort of mistake. And as I mentioned before, we refer to that type of mistake as a type 1 error. So when a researcher rejects the null hypothesis, and they shouldn't have because there's nothing going on in the population, we say they made a type 1 error. Now, in the context of conducting multiple analyses, I point out here that we use the term per contrast error rate, especially in the context of testing the difference between two means or more. So as researchers conduct more and more analyses on the same sample of data, we still consider the per contrast error rate for each individual analysis. And again, researchers tend to specify the per contrast error rate at 0.05, which is the same as alpha for any given one analysis that we might do on one sample of data. So if we were to do 5 statistical analyses on the same sample of data, we would typically specify alpha at 0.05 for each one of those 5 analyses. And we refer to that as the per contrast error rate, or you could say the per analysis error rate. Again, it's a 5% chance of rejecting erroneously the null hypothesis when it is in fact true. Now that's for each individual analysis that a researcher might conduct on the same sample of data. Now things get more complicated when researchers conduct these multitude of analyses on the same sample of data. And what I'm referring to here is the fact that as researchers conduct more and more analyses on the same sample of data, the chances of committing at least one type 1 error increases. It doesn't stay just at 0.05. It actually increases. And we refer to the chances of committing at least one type error amongst a collection of statistical analyses on the same sample of data as family-wise error rate. So the per contrast error rate for any one analysis is fixed at 0.05, but as a collection, all the analyses conducted on the same sample of data, we make reference to the term family-wise error rate. And it's more than the per contrast or per analysis error rate of 0.05. It's actually much more than that. And the formula we can use to calculate what the family-wise error rate is, which is the chances of committing at least one type error across a collection of analyses performed on the same sample of data, is this formula here. It's 1 minus alpha per contrast or per analysis, and it's raised to the power of the number of comparisons conducted, and then you subtract 1 from that result. So here's an example. Suppose 3 statistical tests were conducted on the same sample of data, and the researcher specified per contrast alpha at 0.05. So for any given analysis, the chances of rejecting the null hypothesis when you shouldn't is a maximum of 5%. But what would the family-wise error rate be for that collection of 3 statistical tests? Well, when you plug it into the formula up here, this formula here, when we fill out the numbers, we get the answer of 0.143. So the family-wise error rate is about 14%. There's a 14% chance that one of the 3 statistical analyses is going to reject the null hypothesis erroneously, when it shouldn't have. And I've put together a little Excel sheet here where I can do the calculations for any number of analyses and any per contrast or per analysis alpha level, and we pretty much always have alpha 0.05 for any individual analysis, but the number of analyses we might conduct on the same sample of data can vary widely, and 3 is really not that many. Oftentimes you might have as many as 20 analyses on the same sample of data. That is totally ordinary to see in a publication. So if a researcher published a paper with 20 analyses on the same sample of data, what would the family-wise error rate be? Well, I can just write the number 20 here, and we can see that it goes up to 64%. So there's a 64% chance that one of those 20 analyses reported in the study will represent a type 1 error. So there's a 64% chance of committing at least one type 1 error when we conduct 20 analyses and alpha's 0.05 on the same sample of data. Now, if a researcher had 20 samples of data and they conducted 20 analyses, one for each sample, well then there is no family of analyses on the samples, there's really just one analysis. And so the family-wise error rate stays 5% if you carry out one analysis on one sample of data. It's conducting the same analysis on the same sample of data that is the problem, and that is family-wise error rate. And much research is conducted to help protect researchers from inflating their family-wise error rate beyond the per comparison or per analysis error rate. And much of the textbook's chapter relevant to this topic is devoted to protecting ourselves from inflating our family-wise error rate and making a fool of ourselves by rejecting the null hypothesis when we shouldn't.